SwayamPrabha. Digital India. Educated India.
Hello everyone. In the last class we started to talk about the Fourier series and we started looking at some basics in the Fourier series, right? So the Fourier series representation, it is decided based on the fact that you have a velocity field that is periodic. That is one. So that's the first criteria. So that is what is represented by this equation here, u of x plus n ln, where n is this set of integer vectors and L is the size of the box. So we are considering a flow field that is like a box, essentially a cube, and each side has a length L, and so every L sides, every L times, the velocity repeats itself. I hope that is clear. So that's what periodic means. So we have u of x plus nl equals u of xt. So that was the first criteria, that it had to be periodic. Then we defined some basic things within the Fourier modes. So if you have a set of wave numbers, then and you have the lowest number represented by k kappa naught is equal to 2 pi over L, then you can write the Fourier modes as e to the I kappa naught n1 x1, meaning kappa naught is the lowest wave number, n1 is this integer multiples, and x1 is the first direction. Similarly, you would have e to the I kappa naught n1 x2, e to the I kappa naught n2 x1, x3, I'm sorry, kappa naught n1 x3, so on and so forth. And so e to the I kappa dot x is this expression here, e to the I kappa naught n1 x1, e to the I kappa naught n2 x2, and e to the I kappa naught n3 x3, and so on. Okay. So and also another thing we defined was that the wave number magnitude is the modulus of kappa. Okay, great. The Kronecker delta is defined as follows: delta of kappa kappa naught is equal to 1 or 0. And it is 1 when kappa is equal to kappa naught, and it is 0 when kappa is not equal to kappa naught. That is the basic definition of the Kronecker delta. The orthonormality property we will recall here as the volume average, and that is this new thing that we are defining if we denote this as the volume average. So angle bracket with a subscript L, if we denote that as a volume average over the entire domain, which is our cube. And then if you take a volume average of e to the I kappa dot x times e to the minus I kappa prime dot x, and this with and the volume average of this expression comes out to be the Kronecker delta. Okay, so with that all defined, let's say we define a Fourier series of any real function, which is periodic of course, g of x, and g of x is defined as the Fourier inverse of g hat of kappa, isn't it? G hat of kappa being the Fourier modes of g of x. Now g hat of kappa being a complex Fourier coefficient will satisfy the conjugate symmetry. So g hat of kappa is g hat star of minus kappa. Star indicates that it is a complex conjugate. Minus kappa would be for all the negative wave numbers. Now given g of x, the Fourier coefficients, you can determine it from the orthonormality or orthogonality condition. So if you take g of x times e to the minus kappa prime dot x, volume average of that, and you write g of x as g hat of kappa times e to the I kappa dot x. So this is coming from, this entire thing is coming from here, isn't it? G of x, we are writing it as an inverse Fourier transform by definition. So g hat of kappa e to the I kappa dot x multiplied by e to the minus I kappa prime dot x, volume average L, all right. And then what happens is, remember the volume average is in physical space. We are taking the volume average over the physical cube. So g hat of kappa being in complex space, in Fourier space, you can take it out of the volume average. So if it comes out, and then you're only taking the volume average of this entire expression, which according to the orthonormality condition is delta kappa kappa prime. So then you have g hat of kappa delta kappa kappa prime, which by definition of the Kronecker delta switches the indices, and then you get g hat of kappa prime. So essentially what you've done is you have taken the volume average of g of x times e to the minus I kappa prime dot x, and that comes out to be g hat of kappa prime. So using this, so this is where we were at last time. So using this, we can define an operator, okay? And for now, let's denote it as f kappa. F kappa of g of x. Turns out this is the Fourier transform. So this operator is defined as g of x e to the minus I kappa dot x and volume average of that. Which means, how do you define a volume average? It is 1 by L cube, integral in all three directions. So triple integral. So 0 to L, 0 to L, 0 to L. And then you have the integrand, which is g of x e to the minus kappa I kappa dot x. And then you have dx1, dx2, dx3 for the three directions. This operator operated over g of x is this volume average, isn't it? Which we just proved that it is g hat of kappa, meaning it is a Fourier mode. So essentially, the operator, if you define an operator fk, that happens to be your Fourier mode. So this operator is now defined to be the Fourier mode. Okay. Now, earlier when we were talking about why are we doing all this, why are we trying to convert the velocity space into Fourier space? Why are we taking a Fourier representation of the velocity vector? Why are we trying to, we have not done it yet, but why are we going to try and convert the Navier-Stokes equations into Fourier space? The reason is because it simplifies the way we consider derivatives. This is the reason for developing Fourier transforms. It simplifies obtaining derivatives, and you will see that clearly here. So if I use the operator and apply it on the derivative of g, earlier I applied it on the g itself and it gave me the Fourier mode, isn't it? So now I'm applying it on the derivative. So fk of del xj of g of x. What am I saying here? It is basically del xj is the derivative in the xj direction, right? And I am taking the derivative of a function g of x. It's a real function, and I am taking the Fourier transform of it. Let's see what it is. So I would have, by definition of the operator, by definition of the operator as shown here, it would be, since it is the Fourier operator, since it is the operator applied on the derivative, it would be the derivative multiplied by e to the minus kappa dot x, I kappa dot x, isn't it? It would be the derivative multiplied by e to the minus I kappa dot x, obviously volume average of that, and that's what is written. Now, think about it. I have the derivative of g multiplied by e to the minus I kappa dot x. So, if I want to take a derivative of del xj of, okay, let's say it is g of x e to the minus I kappa dot x. Okay, the derivative of this volume average. So if you consider this expression, now I could apply the chain rule, and it would be g of x, obviously volume average, and then it would be first times the derivative of the second plus second times the derivative of the first. So it would be g of x, okay, times del xj of e to the minus I kappa dot x plus then the derivative, the second one, which is e to the minus I kappa dot x multiplied by del xj of g of x. Obviously x is a vector here, isn't it? And volume average of that. Now turns out the first expression there, So let me just take another page here. I'm sorry. And then go back and then just look at this. Okay. So I have volume average del xj of g of x times x is a vector, of course, e to the minus I kappa dot x. And so this is del xj of this one and volume average of this. Now this turns out this is, okay, this is now going to be del xj of e to the minus I kappa dot x, and this is g of x times this, plus I would have e to the minus I kappa dot x times del xj of g of x. Isn't it? This would actually turn out to be 0, because here I am taking a del xj of g hat of kappa. G hat of kappa is in Fourier space, and I am taking a derivative with respect to g hat of kappa, which is going to be equal to 0. So which means g of x, and that is how I get this expression here. So if I go back, I would have g of x times del xj of e to the I kappa dot x is equal to minus e to the I minus I kappa dot x times del xj of g of x. Okay, it is this expression that I am using here. So I have del xj of g of x times e to the minus I kappa dot x. I will write that as, so that is this expression here. I will write that as minus g of x del xj of e to the I minus I kappa dot x, isn't it? Because the sum of these two turned out to be 0. So one of them would be the negative of the other, isn't it? According to this expression here. So that is what I'm doing. So this can be written as minus g of x del xj e to the minus kappa dot x. Now, in order to take a derivative of e to the minus I kappa dot x, so let me just erase these points. In order to take a derivative of del xj e to the minus I kappa dot x, that will turn out to be, keep in mind, k kappa dot x. Okay, so just so that you know, kappa dot x and obviously I would be, isn't it? It is minus I kappa dot x is in index notation. It is e to the minus I kappa j xj. When I take a derivative of e to the minus I kappa j xj, what I'm going to get, remember, it is only going to be applicable for j. So what I'm going to get is minus I kappa j. I am going to get minus I kappa j. That is essentially what I've gotten here. So I got minus I kappa j. Obviously, because of this negative, it becomes positive as well. So I have I kappa j g of x. Then I have e to the minus I kappa dot x. Volume average of that. I kappa j can come out because that has nothing to do with the physical space. Volume average is over physical space. So I kappa j comes out of the physical space averaging, and then I have I kappa j, and then I have only this part within the volume average. By definition, that is the Fourier operator applied on g of x. By definition, that is the Fourier mode of g of x, which is g hat of kappa, which is what this is. So what have you done? You have applied the Fourier transform operator on the derivative of g of x, and you have gotten I kappa j g hat of k. So essentially, the Fourier transform of the derivative of a function. The Fourier transform of a derivative of a function is I kappa times the function, the Fourier transform of the function itself. the Fourier mode itself. The Fourier transform of the derivative of a function is I kappa times the Fourier transform of the function itself. That's what this is. I kappa j g hat of kappa. I hope this is clear. So this is the biggest benefit of using Fourier transforms. All derivatives have now been converted to some kind of an analytical function. This is how the truncation errors go to 0, because you don't have any derivatives. You don't need to calculate differences between 2 points. It is when you calculate the difference between 2 points, which is when you have to consider whether it has to be first order, second order, third order, so on. And then that brings in truncation errors. In this case, you have a direct calculation of the derivative. Once you get the Fourier transform of the derivative being equal to this one, this expression here, which is I kappa g hat, then you take an inverse Fourier transform to get the derivative back, isn't it? So derivatives were calculated exactly, as in the exact answer of the derivative is calculated. Okay, so essentially that's what I just said. The differentiation with respect to xj in physical space corresponds to a multiplication by ikj in wave number space. What you have done is you have converted your differentiation into a plane multiplication. Now, instead of considering arbitrary functions like g of x, let's consider the turbulent velocity field itself. So I have u of xt, which is equal to the inverse Fourier transform of u hat of kappa, isn't it? So that would be summation of over all kappa e to the I kappa dot x u hat of kappa comma t. And the Fourier coefficients of velocity u hat j of kappa dot t is the Fourier transform of the real space variable, the physical space variable. So this is just an expression where it is shown by applying the Fourier transform operator. That's it. So uj of kappa, okay, uj of kappa is the Fourier transform of uj of x comma t. Remember, the Fourier modes e to the I kappa dot x, they are non-random and they are fixed in time. Whereas here these are random, seemingly random. And so these should be time dependent and random as well, because u of xt are time dependent and random, which means u hat of kappa has to be time dependent and random. Also, we consider the mean to be 0. If the mean of u of xt is 0, it also means the mean of the Fourier modes, as in mean of u hat of kappa, is also 0. And also u hat, which is the complex space or wave number space variable, satisfies the conjugate symmetry, which means u hat of kappa t is u hat star of minus kappa comma t. U hat of kappa is u hat star of minus kappa. So the conjugate symmetry is satisfied. This is the basis now, isn't it? Now we will look at how these Fourier modes evolve in the context of the Navier-Stokes equations. Okay, so we will start with the continuity equation, and according to the continuity equation, I have del dot u is equal to 0. So that means del xj, del uj del xj is equal to 0. This is in index notation, the continuity equation. I'll explain what this figure is in a bit, but let's start. We are starting with the continuity equation, and so divergence of velocity is 0, isn't it? So I have fk of del uj del xj. Now, using what I had just learned as the Fourier transform of del uj del xj, so the Fourier transform of a derivative becomes I kappa j times uj hat, meaning the Fourier mode of the velocity variable itself. So I would have I kappa j uj In vector notation, that is I kappa dot u. In index notation, that is I kappa j uj. By the continuity equation, this has to be equal to 0, isn't it? Because del dot u is equal to 0, k dot u is also equal to 0 because I kappa dot u is equal to 0. So kappa dot u is equal to 0. This is your continuity equation in Fourier space. Kappa dot u is equal to 0. That's what you have done here. You have used the expression related to the Fourier transform for derivative, and you have applied that to the continuity equation, and now you have the continuity equation in Fourier space, which is kappa dot u is equal to 0. That happened because you took a Fourier transform of del xj uj, isn't it? So the continuity equation is set. Now, before we go ahead and convert the momentum equation, the Navier-Stokes equations into Fourier space, let's build a narrative for especially the nonlinear term. Okay, so we will start with an orientation of a vector, and let's take a vector like g hat. Okay, and let's look at its orientation with respect to the wave number vector kappa. Now we can decompose any such vector g hat into a parallel component and a perpendicular component, parallel to the wave number vector and perpendicular to the wave number vector, which means in vector space that g hat is g parallel plus g perpendicular, which is what is drawn here. So any arbitrary vector g hat, okay, it has an arbitrary orientation with respect to the wave number vector. This is your wave number vector, but we decompose the g hat in such a way that you have g hat parallel and g hat perpendicular. G hat parallel is parallel to the wave number vector and g hat perpendicular is perpendicular to the wave number vector. This is the wave number space, kappa 1, kappa 2. Obviously, it's a 3D space, but kappa 3 is not shown here just for simplification. But it's a 3D wave number space, kappa 1, kappa 2, kappa 3. So essentially, kappa vector is kappa 1, kappa 2, and kappa 3. And you have a g hat, which is an arbitrary vector, and a g parallel that is parallel to the wave number vector, and g perpendicular that is perpendicular to the wave number vector. Okay, which means in vector space you can write g hat as g parallel plus g perpendicular. Now if you define your direction cosine E as kappa over kappa magnitude, kappa over the modulus of k, basically that is the unit vector in the direction of kappa, isn't it? That is the unit vector in the direction of kappa. In that case, pay attention here, you have g hat parallel would be equal to, okay, this is what you're going to do. Since it is parallel to the wave number vector, we write it as E dot g because this gives you the magnitude of the vector in the direction of the wave number vector. E is the unit vector in the direction of kappa. E is the unit vector in the direction of kappa. If you dot product E with g hat, what you get is the magnitude of the vector in the magnitude of the vector in the direction of kappa. Then you multiply by E again, being a vector, you will get g parallel. E dot g hat represents the magnitude of the vector in the direction of kappa, as in parallel to the direction of kappa. You multiply by E again and you get the vector itself. Then what do? You substitute for E, you substitute kappa over kappa magnitude. You will get a kappa magnitude squared in the denominator, which is what this is. And then for kappa here, You would have kappa dot g, because for the E dot g, and then the E outside will give you another kappa. So you have kappa times kappa dot g divided by kappa squared. That is in vector notation. In index notation, this means that G hat parallel would be, okay, so kappa dot g, remember kappa dot g in index notation is kappa k gk. You multiply that by another kappa and then you have a kappa j, because kappa k gk is your dummy index. So this part here becomes actually kappa k gk divided by kappa squared, isn't it? This is kappa squared, and because you have a kappa on the outside, it would be kappa j, and this would be equal to G parallel j. You see it? So G parallel j, obviously hat because it is in Fourier space, is equal to kappa j kappa k divided by kappa squared multiplied by gk hat, of course, in index notation. I am writing this partly as a vector and index as kappa j kappa k over kappa squared times g hat. Okay, so what we have done here is today is we have used the definition of the Fourier transform and the fact that the Fourier transform for derivative becomes equal to I kappa times the Fourier mode itself. We have applied that to the continuity equation, and now we are starting to build that for the Navier-Stokes equations. In the next class, we will continue from where we had left off and finish up the derivation of the Navier-Stokes equations into Fourier space. Thank you.